Okay, I'm now going to talk about some mechanisms that generate power laws. Now, this is quite similar to models, but the reason I called those models and these mechanisms is that with the models, it's very clear sets of equations that generate power laws in a very definite way. With mechanisms, we start with pictures of processes that can occur and that we know tend to generate power laws. And then there have been developed mathematical models to explain why those power laws occur, though there are questions about whether those models really are accurate descriptions of the process, or those models are very complex, or those models may only work under certain circumstances, and so on. So these are more messy perhaps than our models. But again, they are processes that we know can generate power laws. And so if we see power laws in our socio-historical data, we can start to think about whether one or other of these mechanisms might be at work. So what I'm going to do is just say at a high level what each one is, and then we'll go through each one in detail. So the first one that we'll look at is what's known as a multiplicative process. So here we imagine the items that are subject to our power law distribution as being capable of growing or shrinking by a random factor at intervals, at multiple time steps. So it might be, for example, cities. They can grow or shrink by having people move in or move out of the city. And they increase or decrease by a random factor that is independent of the size. So it might be, say, 10%. So if it's a village of 1,000 people, it grows by 10%, it gets an extra 100 people. Or it might be a city of 1 million that grows by 10%, so it gets an extra 100,000. But it's the factor that is independent of the size. So we're multiplying by a certain factor rather than adding a certain amount. So we're not sort of adding 100 people at each time step. We're multiplying the existing size by a certain random factor. So our items can grow or shrink by a random factor and that's what makes it multiplicative. So if we were adding amounts, that would be an additive process, but we're growing and shrinking it by a random factor. That's what makes it a multiplicative process. And then it's subject to constraints. And typically the constraint is that the total population of the country, if we're talking about cities, remains the same. So individual cities can grow or shrink as people move in and out, but the overall population of the country remains the same. And if that is the case, then we find that in the steady state, it will result in a power law. And we will see a mathematical derivation of that. Our next process is what is known as preferential attachment. So this is also known as the rich get richer effect. So again, if we're talking about cities, big cities are more likely to attract more, new immigrants. If you're deciding to set up a restaurant, it kind of makes sense to set up your restaurant in London, where there are lots of potential customers, rather than in the Outer Hebrides, you know, where there's very sparse population. So when people are setting up restaurants, they're more likely to go to cities that are already large, and those cities will therefore get even larger as they, you know, set up their restaurant, create their business, start to employ people and bring people in for those jobs and so on. So preferential attachment is a get richer effect. Some people also call it the Matthew effect. After the Gospel of St. Matthew, which says somewhere that to those that have, more shall be given. And the particular model we'll be thinking about for this is about networks that are growing by the addition of new nodes to the network. An example, or you know, that's a bit like academic citations. So you know, we've got a network, and we can add a new node, and it's going to, well, let's put, there's a node that's already got a lot of attachments, and this preferentially attaches to a node that has already got a lot of attachments. That's like I was saying, people are going to go to London, not to, you know, some remote village in the Outer Hebrides to set up their new restaurant. So our model for thinking about this is in terms of these networks. And I said it was like academic citations because citations form a kind of network, because academic papers are joined to other papers that they cite. So and then if people are you know, reading papers, they're more likely to find out about papers that already have a lot of citations, because those will be mentioned in many papers and be in people's bibliographies. So they're more likely to come across them and then cite them themselves. So we find that in the citations, or the number of citations that academic papers get, there is a power law, and so this preferential attachment is an explanation for why that is. So some papers get a lot of citations. It's because of this get richer effect, and ones that already have citations will get even more citations. And the last mechanism we will consider is what's known as a sample space reducing process. And our mental picture for that, oops, I'm trying to draw a staircase here, is of a ball bouncing down a staircase. And you know, it can jump by random amounts down the steps. So you know, it might go on to the next step, or it might bounce for 3 and so on. And all the ball and the ball ends up here at the bottom. And we then imagine doing this over and over again, sending thousands of balls down this staircase. And the question is, how many of the balls bounce on each step? Well, if we call that step 1 at the bottom, all the balls end up there. So all the balls will bounce on the first step. And what we find is, and we're going to do this, the maths in a bit, is that half the balls will bounce on the second step. A third of the balls will bounce on the third step. A quarter of the balls on the fourth step, and so on. And that may remind us of what we saw with Zipf's laws, that if we've got in the distribution of items, we talked about, say, for example, New York City being the biggest city. And then if this law applies, the second biggest city is half the size of New York. The third biggest city is a third the size of New York. That is a result of the fact that they obey a power law. We showed how a power law leads to that conclusion if the exponent of the rank size plot is -1. Well, what we see here with this sample space reducing process is something very similar. All the balls there, half them here, a third here, a quarter here. So it's like the number of balls bouncing on each step is very like the sizes of the cities obeying a power law. So the how many balls bounce on each step also obeys a power law. And this kind of thing has been suggested it might explain, for example, power laws in language. If we think of forming a sentence, it's a bit of a sample space reducing process. Perhaps I should have said this is called a sample space reducing process because when the ball is at the top, it could bounce on any step. They're all below it. But once it's got here, it can't bounce on these ones back here. It can only now bounce on the things below it. So at each bounce, it reduces the number of places it can go to, the number of possible next bounces. So it's reducing its sample space. And so with language, forming a sentence is a bit similar. That once you've chosen a word for your sentence, it kind of restricts the other words that could come next that would still make sense and make a sensible sentence. So that as you are forming sentences, you're kind of bouncing down a staircase, and by the time you sort of get to the last word, it's you're pretty much constrained as to what possible word could go in there that would make sense. When I said it produces the pattern of all of them here, half here, a third here, a quarter, that's with an exponent of in the power law of -1. But in fact, you can generalize this, have the idea of a free move where at random intervals, the ball, instead of bouncing down, can move to any step, up or down. And if you give that a probability of 1 minus lambda, then you can get an exponent, power law exponent of minus lambda instead of just -1. And so you can get power laws with other exponents if you introduce this idea of a free move. So it's a bit more general than it initially seems. So I said we would start with a multiplicative process. So we're going to use as our mental model cities that can grow or shrink as people move in and out. And we're going to say that at each time step, let's say each year, they have grown or shrunk by a random factor that doesn't depend upon the size. And we're also going to have the constraint that the total population of all the cities added together is fixed. It remains the same. The population of the country remains the same. And we're going to think about this starting with a very simple illustration, and then we will generalize it to the general case later. So firstly, starting with a simple approach, just to give us a bit more of an intuition as to what the argument is and what's going on. So I'm going to imagine 3 levels of cities, and we'll say this level, cities at this level have a population of 1, which might be 1 million. So these are cities of 1 million population. These lines don't really mean much, except that they're just levels of cities. These are larger and these are smaller, because what we're going to say is that cities can grow or shrink by a factor of 2 at each time step. So our factor is going to be 2. It's not going to be a random value. That we'll consider that when we go to the generalization. But these can just grow or shrink just by 2 at each time step. So if we've got cities of 1 or 1 million, then at the next time step they could double in size to be cities of 2 million. Or they could shrink by a factor of 2, and then they would be half. They would be 500,000. So we're only ever going to have cities at these levels because they can only double or halve. So from there they could. I mean that the levels will always be powers of 2, because from here it can then double again to be 4, or it could halve again to go back to 1, and this, if it's halved, then it could halve again and become a quarter. But we'll only have these discrete levels, and I'm just going to consider 3 of them here. And then we can say that the number of cities of size 1 is n of 1. The number of cities of size 2 is n of 2, and the number of cities of size 1/2 is 1/2. And we're interested in how this number depends upon the size of the city. That's, like our old power laws. The number of a particular size is proportional to s to the minus alpha. That's how we start in considering power law distributions. And what we're going to show here is that indeed this scenario results in a power law distribution like that. So at each time step, the cities can either grow or shrink by a factor of 2. They can either double, and we'll say that has a chance of p, a probability of p, or they can shrink, and that is 1 minus p. So they can't stay the same. They either grow or they shrink. And we now know that, or we know that let's consider the average size of the cities, these cities. Well, all these cities at the moment are of size 1. So the average size is 1. And what we're going to say is that the average size of these cities must remain the same after this process of growing and shrinking. Because if there was a tendency for the average size to increase, that would apply for all the levels, because they're all subject to the same principles. So the average size of the cities at all levels would be increasing, and that would mean that the total population would be increasing, which cannot happen because we've said that the total population is fixed. So the average size of the cities must remain the same. Well, the average size is going to be, after the time step, a fraction p of them have moved up to be of size 2 now. So there's p times n of 1. I'll put that in there. There are n1 cities, so a fraction p of them, p times n1, have increased in size to size 2. So there's p of n1 times 2 in population, and there's 1 minus p have shrunk to be 500,000, size 1/2. So there's plus 1 minus p times n of 1 of size 1/2. And to find the average, we divide by the total number of cities, which is just the same. There were n1 of these cities that we said at this point, and so we're considering what their average size is after some of them have moved up to there and some have moved down to there. So that is, in other words, just 2p plus 1/2 into 1 minus p, and that is equal to 2p plus a half minus a half p. And this is, remember, 1, the average size started as 1, and we're saying it's got to stay the same. So we can put this half on this side. We've got a half equals 2p minus a half p, so that's 3 halves p. So p is equal to a half divided by 3 halves, which is equal to a third. So to keep this steady state, it must be that the probabilities of growing or shrinking must be a third. So that's going to be one third grow and 2/3 shrink. And the same will apply at every level, because the logic is the same. At every level, it's always the case that they can double or halve. Now, the other thing, though, is we consider that we've got to keep the same number of cities in each level as well. That must be constant in the steady state, because if there was a tendency for any reduction in the larger cities and for the lower numbers to increase, then all the cities would be getting smaller, and again that would imply that the population was getting smaller, which can't be, because it's got to remain the same. Or alternatively, if there was any net tendency for cities to grow in size, so that the numbers in the upper levels increased over time, then the cities would on average be getting larger, and again that would imply that the total population was getting larger. So that can't happen. So these numbers have to remain the same in the steady state. So the number of cities going up must be balanced by the number of cities coming down, and the same, the number of cities coming up from here must be balanced by the number going down. Though we only need to consider this particular one here. So the number of cities going up is p times n of n1. There's the chance of 1/3 of them doubling in size, so 1/3 of n1 increase, go up in size, and 2/3 of these n2 cities shrink, and so they must equal. As we've just said, these have got to balance. The cities moving up the levels have got to be balanced by ones moving down the levels to keep the steady state. So that tells us that if we take this on to over here, that let's put n2 equals a half n1. If we take 2/3 down here, we got a third divided by 2/3, so that's a half, but I've just also swapped it around. So n of 2 equals half of n1. Now, the same would be true of the number of cities of size 4, just by the same logic. They would have to be half the number at this level. So n at 4 is going to be half of n2, or in other words, it's going to be a quarter of n1. And then the number of size 8 is going to be, again, half. So it's going to be 1/8 of n1. And in general, the number of cities of size 2 to the n is equal to 1/2 to the n times n1. So the number of cities of size s is equal to 1 over s times n1, which is n1 is a constant, it's some value. So in general, we have the number of cities of size s is proportional to 1 over s, which is s to the minus 1. So we have a power law. That's minus 1. We have a power law, and in fact it's a power law with an exponent of minus 1. So this is an example of a multiplicative process, and all our arguments were based upon this principle of there being a constraint that the total population has to remain the same. And if we satisfy that constraint, we're forced to have these probabilities of going up or down, and we're then forced to have this relationship between the numbers in each level of city. And it is a power law in the size of the city. So, as I say, that's a kind of simple argument to get the feel for the more general argument that we're going to have a look at now. What we're going to say is let the probability of growing by f be p of f. And we must have also the average growth of all the cities is equal to 1. This is our constraint. Although some cities are shrinking and some are growing, overall the total population is not growing or shrinking, it's remaining the same. So on average, the growth must be equal to 1. So we want to consider this average growth. And to do that, we're going to find the fraction that grow by each factor and then add those all up. And that will be the average. So we're kind of, as I said earlier, we're kind of jumping ahead to things we will be considering more in the statistics part of the course, but we do need them now. So you know, I'm relying on things that we'll be covering later. I'll sort of just talk through what I'm doing, but you know, if hopefully you just bear with me at the moment. If if you'll have issues with it, we will discuss these things later in more detail in the statistics part. But so the average growth is going to be taking each possible growth factor and multiplying by the fraction of cities that grew by that factor. Well, it's the probability of growing by that factor, but it's P of f df, because remember this is a probability density. So the actual probability around f is P of f df. So we're looking at the cities that grew by factor f. They had a probability of f df of growing by that factor. And to find the average growth, we're going to add up all those the factors that so many fractions of the cities grew by these factors. We're going to add up all the possible factors, and then the fraction of cities that grew by that is going to be the average growth. So we're going to integrate that from 0 to infinity. The factor of growth could be, in principle, be anywhere from 0, shrinking to 0, up to growing to infinity. And we're saying that that equals 1. So it's not something we need to calculate, but we're just saying that the probability of growing or shrinking by, or growing by a factor f, because f could be less than 1, so that would be shrinkage. The probability of f has to function in such a way that this integral holds true, equals 1. So that we can kind of take as read. That's our kind of constraint expressed in those terms. Now let's assume that we have a cumulative distribution function p of s. Remember that this refers to the probability that a city is of size s or greater. And this must remain constant, because if there were a tendency for it to increase, then it would mean an increasing proportion of cities were above size s. And that would mean that on average cities were getting larger, which cannot be. The average growth is 1. So P of S can neither increase nor decrease. It must remain the same in the steady state, so that the number growing is balanced by the number shrinking. And now let's think about cities that grow by a factor f. So there are P of f times df of those. This is the fraction of cities that grew by a factor f. And what's the chance that they would now be of size s or larger, so that they would contribute to this P of s, that they would be above the size of s? Well, to be above the size of s, to be s or greater, they would have to be of size s over f before, because they've grown by a factor f. So to be of size s after they've grown by a factor f, they must have been at least of size f, because f times s over f equals s. If they were larger than s, then if they were 2s and we multiply by the factor f, then there would be 2s, so they'd certainly be above. But the minimum they could have been is of size f, size s over f, to become size s after they've grown by a factor of f, multiplied by a factor of f. So how many of those are there? Well, it's just P of s over f. That is just like this is the probability or the fraction of cities that are s or larger. This is a fraction of cities that are s over f or larger. So this is a number of cities that grow by a factor f, or the fraction of cities really that grow by a factor f. And this is the fraction of those cities that now are of size s, s or greater. And so if we add all those up, in other words, integrate this for all the possible factors f, then those will be the cities that are at least of size s or greater. In other words, this integral must be P of s, the fraction of cities that are s or greater. So just to repeat that, these are the cities, the fraction of cities that grew by factor f. This is a fraction of those cities that are now of size s or greater. And if we do add those up for all the factors, we get all the cities that are at least of size s now. Well, let's now assume that we do have a power law. So we're not going to derive it, but we're going to show that a power law satisfies this situation. So we'll assume a power law. So we'll assume that P of s equals cs to the minus 1. So in fact we're assuming a power law in the cumulative probability of with an exponent of minus 1. C is a constant. So for this to be consistent, because we said that P of s must remain the same, so we're going to have here cs to the minus 1 equals the integral from 0 to infinity of P of s over f. Well, it's going to be c times s over f to the minus 1 times p of f df. Now f is the only thing that's changing in here. It's the variable. So we've got to leave f inside this integral, but c and s are just constants, so we can bring those out. So the c we can put in front of the integral, bring it out to the integral, and the s is just a constant, so we can bring it out to the front, but it's s to the minus 1 here, so it's cs to the minus 1. Integral from 0 to infinity. Now we've taken the s out, so we've just got here left 1 over f to the minus 1, and then p of f df. And that is equal to cs to the minus 1 times the integral of 1 over f to the minus 1 is just 1 over f, so that is just f, and then p of f df. But this thing we had up here, that's our constraint, is just equal to 1. So this is equal to cs to the minus 1. And therefore that is consistent. We said that ps must remain the same, and if we have this form for p of s, cs to the minus 1, then this equation is satisfied. And with a bit more advanced mathematics, you can show that not only does this power law satisfy this equation, but it is the only thing that satisfies it. So in other words, we've shown that with our assumptions of a multiplicative process where the probability of growing by a factor f is the same for all cities, then and with this constraint that the average growth is 1, so they neither grow nor shrink overall, then a power law is the only thing that will satisfy these constraints. So in other words, as cities are growing and shrinking, they will tend towards forming into this power law when they reach a steady state. What people have pointed out that though is that although this could explain why cities obey a power law, in principle it doesn't seem to work in practice, because if the cities don't start off in a power law, it can take them a very long time of growing and shrinking to end up in a power law. It takes a very long time to reach that steady state. Whereas, you know, we see power laws in existence in the sizes of cities all around the world. So, you know, it's not taken them very long times to reach those configurations. So this is in principle an explanation, but it's probably not the explanation for why cities obey this power law. But it is nevertheless a mechanism that you know, is worth thinking about, possibly for other situations. Okay, so our second mechanism is preferential attachment. This is the rich get richer effect. So our mental picture for this is a network consisting of nodes attached to other nodes, which are themselves attached to yet other nodes. And what we're going to be adding a new node to this network at every time step. And we're going to do it so that we preferentially attach the new nodes to nodes that already have a large number of links or connections. Now, the number of connections of a node is known as the degree of the node. The connections equals the degree of the node. And if we call this node I, then we'll say its degree is ki. So k for the degree, or ki for the degree of the kth node. So in this case, it has a degree of 5. And our goal is to show that there is a power law in the degrees of all the nodes as a result of this process that we're applying. So what we want to show is, and we're going to use, we'll use probabilities in this case rather than pure raw numbers. The probability of a node having degree k is proportional to k to the minus alpha, where alpha is some constant exponent that we're going to try and find out. So that is a power law, and that's what we're going to try and prove, that this process of adding nodes, preferentially attaching to ones that already have a large number of connections, will produce a power law with a few very well connected nodes and many less well connected nodes. And the first thing we're going to do is try and develop a formula for how the degree of a node depends upon the time. So to start with, we're saying that the probability of attaching to a node depends on its existing degree. So the higher the degree, the higher the probability of attaching to it. So the probability of attaching to this node I is proportional to ki. And we need the probabilities for all the nodes to add up to 1. So to turn this into an exact formula for the probability, we need to divide by the total degree of all the nodes. So the probability of attaching to a node is equal to its share of the whole degree, or the share of its degree of the total degree of the network. And then if we add up all the probabilities here, we'll be adding up these ki's, and that will be the total degree of all the nodes added together, and then we'll be dividing by the total degree, so that will equal 1. So this is the appropriate formula for the probability of attaching, which creates this preferential attachment. It depends on the existing degree, and this degree of course is changing over time as we're adding new nodes, and some of them will be attaching to this one. So as I say, we're going to try and find a formula for how ki varies with time. Now the total degree of all the nodes, well, we're adding one new node at every time step. So if here's a new node, and let's say we connect to that one, each time we add a new node, we increase the total degree of the network by 2, because the new node creates a link which creates a connection between two nodes. So if we're adding this one here, this one now, its degree has gone from 5 to 6, and we've also added a new node with degree 1. It's just got one connection. So we've added 1 there and 1 there, so we've added 2. So we're adding 2 degrees to the network at every time step. So after time t, the total degree of all the nodes will just be 2 times t. So our formula for the probability of adding to the node is ki over 2t. Now, each time we add a node then, we're adding one node at each time step. So the probability is pi that it attaches to this. So on average, at each time step, we'll add pi of a node to this one. And in dt time steps, we'll add pi times dt. new nodes to this one. So we can say that the change in the degree in time dt, that is, we're going to add dt new nodes, is just pi times dt. Because we've added dt new nodes and there's a probability pi that each one attaches to this one. So it's pi times dt will be the net number added to this one. You know, so if we're adding 100 nodes, that's dt is 100, and there's a 1 in 6 chance that they're attached to this, then it will be 1 in 6 times 100, 1/6 of 100. You know, 16, 17 new nodes. So in general, the change in the increase in the degree of the node is a probability of adding a new node to this one times the number added to the network, which is dt in time t. So we can then substitute in our pi. So we've got ki over 2t times dt, and we can rearrange this a little. We've got dki here, we can bring this ki down. We've got a half in front, so let's put that. We've got dki over ki equals a half times dt over t. And now we remember that we can express dki over ki as d of log of ki equals a half times d of dt over t, that's d of log t. So when we integrate this d log ki, we're going to get log of ki, and that's going to be equal to, integrating this side, we've got a half times log t. And then we also need to add a constant c, and that will depend on the node, so we'll write that as ci. And then we can exponentiate both sides of this to get from log ki, we can get to ki. So raising e to the power of this and raising e to the power of this side. So that's going to be t to the half. So that's just remembering that m log x equals log of x to the m. So a half log t is a log of t to the half. So when we exponentiate it, we'll get t to the half. And then plus ci, well, that will become times, because taking logs makes multiplication into addition. Doing it the other way around makes addition into multiplication. Ci, this will be a constant times ai. I'll write it as, where ai equals e to the power of ci. So in fact, we could just put that the other way around here. So the degree of the ith node is equal to ai, some constant, times t to the power of a half. So the question is, what is this constant? Well, you know, constant of integration, we need to consider initial conditions. So let's suppose that the this node is or joins the network at a time ti. You know, or is created at time ti. Well, when it's first created, it will only have degree 1, just like this. It's a baby node that's just been added. It will just have degree 1. So at time ti, which is when it joins the network, its degree will be 1, and that is equal to ai times ti to the 1/2. So ai equals 1 over t to the 1/2. Oops, ti to the 1/2. So our final formula for the degree of the node is ki equals t over ti to the 1/2. So we now have an expression for how the degree of the node depends upon time, and also this constant, which will be different for each node, but is the time when that node joins the network, or when it's first created. Okay, so let's clear that up to give us some more space, and then we can carry on. Okay, so that's what we've just derived, that how the degree of the ith node depends upon time. And what we want to do now is try and get an expression for this p of k, the probability that the node has degree k. Well, the way we're going to do that is perhaps seems a little roundabout, but firstly we'll consider the probability that the degree of the node ki is less than some value k. And this is a cumulative probability. So it's a bit different from the ones we did before, considered before, where it was a probability that it was above a certain value. This time it's the probability that it's below a certain value, but it's still a cumulative probability. And this is going to be equal to then the probability that ki is t over ti to the 1/2 is less than k. And now we can rearrange this a bit. If we square that, we'll get t over ti is less than k squared. And we can then put the k squared down here and the ti up there. And we'll get ti is greater than t over k squared. So let's do that. Oh, it's done a rather large number of steps in one, but so that is the same as the probability that ti is greater than t over k squared. Yeah. And then we'll say that this is equal to 1 minus the probability that ti is less than or equal to t over k squared. So ti is either greater than or less than or equal to. So those two probabilities are complementary. The probability that it is that is 1 minus the probability that it isn't that. And then this is something that we can start to work out. So we're asking, what's the probability that the time when this node was added is less than or equal to t over k squared? So let's just write that down again. For the probability ti is less than or equal to t over k squared. Well, that is equal to the number of nodes added before t over k squared, or before and up to, let's say up to, it's less than or equal to, divided by the total number of nodes. And both of things are very straightforward to work out, because there is one node added every time step. So after t time steps, there will be t nodes. So the total number of nodes is just equal to t. And similarly, in the first t over k squared time steps, there will be t over k squared nodes added, because there's one node every time step. So in t over k squared time steps, there will be t over k squared nodes added. So that just comes to 1 over k squared, cancelling out the t's, or k to the minus 2. So this was to do with this probability of ki is less than k. So we can now write that the probability ki is less than k. We worked out that it was 1 minus this, and we've just worked out that this is k to the minus 2. So that is equal to 1 minus k to the minus 2. Now the the problem is that we've got here a cumulative probability, and we're trying to work out the probability density P of k. Well, we can call this cumulative probability just P of k. So P of k is the cumulative probability up to k. So it's the probability that the node is less than k. So if we draw along here the values of k, which you can say go from 0 up to, well, let's actually write this is, since we're using k as the degree that it's less than, so I'll just call that's the degree, which varies from 0 up potentially up to infinity. And when we're talking about P of k, it's the probability of lying in this region, anywhere between 0 up to k. So it's a probability that ki is somewhere in this region. And then if we consider P at k plus dk, so this is d P of k. This is the change in P of k as we go from k to k plus dk. The amount of probability in that space is, if that's dk, times the probability density P of k at k. So that is how much probability is in that little region from k to k plus dk. So we can see from this that the change in the cumulative probability is just equal to dk times P of k. That's how much we've added to the cumulative probability when we go from the probability up to there to the probability up to there. So we can see from this that then what I've said is that dP of k, I'll leave out the k, is equal to P of k, and again I'll leave out the brackets k, P times dk. So in other words, P equals dP by dk, which is fairly predictable from the fact that the cumulative probability is an integral of the probability. So is an integral of the probability density. So the probability density is the opposite of an integral, which is the derivative of the cumulative probability. So that's what we're saying here. So to finish off then, P of K, that's what this is, P of K, the probability that Ki equals K, is a derivative of this, P of K. So the derivative of 1, that's 0, that just disappears, and K to the minus 2, we subtract 1 from the exponent and bring that down. So it'd be minus 2 times, but we've already got a minus sign there, so that would be just 2 times K to the subtracted 1 minus 3. So in other words, P of K is proportional to K to the minus 3. And so we've achieved what we set out to do. We've shown by this argument that the probability that a node has degree K is proportional to K to the minus 3. So it's proportional to K to the minus alpha, where alpha is 3. So we've got a power law. Now, it's not a very pretty argument, but it's an argument to suggest and justify why we would expect to find power laws as a result of this preferential attachment process. And the fact that there are power laws, we can regard that as an empirical result, maybe. From computer simulations that have been done of preferential attachment and then measuring the degrees of the nodes, and also from the fact that academic citations, which are very similar to this model, where new papers attach to existing papers and preferentially attach to ones papers that are already well known. If we find power laws in academic citations, then we can say that preferential attachment kind of leads to power laws, and then we've provided this argument as to why that is the case. And I wouldn't suggest that this is something one feels one needs to know and understand and carry around in one's head. The main point is to know about this idea of preferential attachment and its ability to produce power laws, so that when in future in socio-historical systems we see power laws, we can say, could this be a case of preferential attachment, and get the cogs of our brains thinking about whether some kind of process like that is going on. It could be, though, a multiplicative process, what we've just seen earlier, but this is another string to our bow, another thing that we can look out for. And the concept of preferential attachment is fairly straightforward, that we just it's a rich get richer, that we attach more to things that already have a lot of attachments. That's pretty easy to remember and understand. All this mathematical justification just shows that there is a mathematical justification to it. You may never actually need it, but what is useful to know that there is one, so that if you do find you want to try and understand a bit better, or maybe adapt this derivation to a different situation, it's there as a resource. And it's also just for completeness, rather than just telling you that it produces a power law. It's nice to kind of justify it. And perhaps one last thing to say on this is that in this preferential attachment process we've described, we start nodes at random times. So we add them to the network at random times, and then we allow them to grow in an exponential way, because they grow at a rate that is proportional to their existing size. The bigger they are, the faster they grow. That's the basic formula for exponential growth. So they're added at random times, and then they grow exponentially. And some people have tried a kind of reverse of that, which is to start off with a lot of things that grow exponentially, and then stop them after random times. So some of them are stopped early and so they'll be quite small, but others are randomly allowed to go on growing much longer, and they'll be growing exponentially, and when they're stopped they will be very large. So it's kind of the opposite of this. Instead of starting at random times and growing exponentially, we grow exponentially and stop at random times. And that also leads to a power law. So again, if you find power laws in socio-historical processes, you can think of this preferential attachment process, or you may think of the kind of process I've just described. Is this caused by things that are growing exponentially and then being stopped at random times? And some people have suggested this might be an explanation, for example, of power laws in people's incomes. It's as though everybody starts out in life growing their income exponentially, but some people achieve their potential early, but others keep going and keep building their fortunes, and so the growth stops at random times for different people, and so we end up with a power law in people's incomes or people's net worth. So our next mechanism to consider, and the last one, is the sample space reducing process. And that is based on this idea of where we have a ball bouncing down a staircase. And it can take many paths, and we're interested in what is the probability that the ball bounces off or visits any particular step. And we can call this step at the bottom step 1, and all the balls end up on step 1, the lowest level. And what we're interested in is what is the chance that it visits step I on its way down. So to start with, let's define pk of I as the probability that the ball with k steps below it visits step I. So that's just a definition. And now let's suppose that we're on step n plus 1. So we've got a staircase with n plus 1 steps. We're on n plus 1. So that means there are n steps below us, 1 to n, and we're in n plus 1. So there are n steps below us. N steps. And we're going to be interested in, with this n steps below us, what's the probability of bouncing off step I, Pn of I. We've got n steps below us, so it's a probability that a ball with n steps below, instead of k, visits step I. That's Pn of I. So that equals what? That's what we want to know. Well, there are two ways that the ball can end up on step I, which is go direct to step I. So it could just bounce directly, or it can go to another step, J, let's say here J, then to step I, where J has obviously got to be somewhere above I. Well, what are the probabilities? Well, the probability here, going directly to step I, there are n steps, so the chance of landing on any one of them is 1 over n. So the chance of going directly to step I at the next bounce is just 1 over n. And then the chance that it goes to step J, then to step I, not necessarily directly, it could bounce a few more times, but the chance that it goes to step j first and then subsequently to step I, well, firstly is going to be the probability that it lands on step j, so that's 1 over n as well, so the chance that it visits step j is 1 over n. And then we need to multiply that by the probability once it's on j that it visits step I. Well, if it's on step j, that means there are j minus 1 steps below it. So using this definition here, the chance that once it's on step j it visits I is just p of j minus 1 of I. So if it's on step j, k, the number of steps below is j minus 1, so pk of I, pj minus 1 of I. And now j could be any step above step I. So j can go from I plus 1 up to n. So we've got to consider this for all the steps from I plus 1 to n. So j can vary from I plus 1 to n. So that gives us that the probability Pn of I is equal to these two probabilities added together. So that's 1 over n plus the sum for all the possible j's, which we said was some j equals I plus 1 to n of this. So that's 1 over n times p j minus 1 of I. And now what we're going to do is do a proof by induction. So we're going to assume a form for pk of I, and we're going to show that if this form we assume applies up to a certain value, then it applies for all values above that. And then we'll show that it applies for the minimum possible value. And so if it applies for the minimum possible value, and we've shown that if it applies for any value, it applies for everything above, then we've shown it in general for everything above the minimum. So that's the normal logic of a proof by induction. So for what we're going to do, the proof by induction, we're going to assume that a particular form for pk of I has been proven, and the form we're going to assume is just 1 over I. So we're going to go straight to assuming it is a power law. And we'll assume that that has been proven for k up to and including n minus 1. So if we take that assumption, we can now look at this again. 1 over n times pj minus 1 of I. Well, pj minus 1, the maximum value that j minus 1 can take on is n minus 1, because j goes up to n, so that will be pn minus 1. And we're assuming that this has been proven up to n minus 1. So we can just put for this 1 over I for all of them. They'll all be equal to 1 over I, all the way up to n minus 1. So that is times 1 over I. Now we can take out the 1 over n factors, so we've got 1 over n into 1 plus the sum from I plus 1 to n of 1 over I. Now remember, it's j that's varying here, so there isn't a j in here. 1 over I is just a constant. So we're adding up 1 over I how many times? Well, between I plus 1 and n, there is n minus 1 steps. From step I plus 1 to n, there is n minus I. Did I say n minus 1? I meant n minus I. So that is equal to 1 over n into 1 plus, we said there's n minus I of those. So that is equal to 1 over n into 1 plus n minus I times 1 over I is n over I minus I over I, which is minus 1. So it equals 1 over n times n over I equals 1 over I. So if this is true for k up to n minus 1, then it's also true for k equals n. And then by implication, if it's true for k equals n, then it's true for k equals n plus 1. So it's true for anything above that. So now let's consider if we're on step I plus 1 here. So we're interested in p of I plus 1 of I. Well, if we're on step I plus 1, what's the chance of going to step I? Well, there's nothing in between, so we can't sort of bounce on an intermediate step. So the only option is to go directly to step I. So that has a probability of 1 over n, or 1 over the number of steps. And what is the number of steps below I plus 1? Well, it's simply I. There are I steps up to I plus 1, from 1 up to I. So if we're on step I plus 1, then p of I plus 1 of I equals 1 over the number of steps, which is 1 over I. So we know that for this step, the lowest step above I, that this formula holds. And we know that if this formula holds for any particular value k, then it's going to hold for everything above k. So for this step, the probability of visiting there is 1 over I, and the same is true for all the other steps. So if we're on this step n plus 1, then the probability of visiting step I is just 1 over I. And so we have, in general, then, so in other words, this assumption that we built in here is actually correct. We can't talk about the probabilities for anything below I because they don't have any chance of visiting I. But for anything above I, it's true that its probability of visiting I is 1 over I. So Pn of I equals 1 over I, or P, probability of visiting step I from any step above I, is proportional to I to the minus 1. And so there we have a power law. And as we said, what that means is that all the balls go to step 1, half of them will go on step 2, a third will go on step 3, a quarter will visit step 4, and so on. And so this is a possible model for power laws in socio-historical processes, that we might be able to see them as sample space reducing processes. You know, the whole of social evolution could be seen like that, that when your society develops certain institutions, that reduces the options for where you go from there. You're going to be developing things that are got to be consistent with what you've done already. So the whole of social evolution is a sample space reducing process where you're reducing your options for further movement. And so we might then expect to see some kind of power laws in the processes of social evolution, for example. And this is, a very special case where it's just proportional to I to the minus 1. I said, when just gave the overview of these, that if you assume the possibility of a free move every now and again with a certain probability, you can get other exponents, not just one, but it could be I to the minus lambda, where lambda is some other value. So you can get arbitrary exponents out of this by assuming this idea of a free move. And you can also consider things like, what happens if the steps aren't the same size? And in fact, what you find is that if the steps aren't the same size, actually, it's still true that it's 1 over I if you don't have free moves. And there are other variations that have been tried on this sample space reducing process. So this is the basics, and then you can kind of elaborate on this to explore other possibilities and maybe get other kinds of behaviour. But this is what we need to know for now, that there is this idea of a sample space reducing process. It's a mechanism for generating power laws, and so when we see power laws in our socio-historical data, we can say, is this a sample space reducing process? Possibly.